You've probably already noticed that there's a strong connection between the properties of neurons that we've talked about so far and the terminology and theory of electronics. For instance, we've already talked about one connection to electronics. We've seen how concentration gradients and semi-permeable membranes give rise to a membrane potential, which operationally, if not mechanistically, behaves like a battery insofar as it generates a voltage across the membrane. There are two additional important ideas from electronics that have direct analogies in the neuron and that are essential for understanding the neuron's function: resistance and capacitance. Let's start with resistance. Resistance is basically what it sounds like: a quantity that describes how much a conductor opposes the flow of charge through it. The flow of charge through a conductor, incidentally, is called current, and it's usually represented by a capital letter I. Resistance is fairly intuitive. In electronics, if we have a thick wire, it's easier for current to flow than if we have a small wire, since there's more cross-sectional area for the charge to flow through. We'd say that the big wire has a lower resistance, and the thin wire has a higher resistance. Conductance is the inverse of resistance, so the big wire has a higher conductance, and the thin wire has a lower conductance. Different materials are differently conductive as well. Copper, for instance, has a much lower resistance than, say, salt water. In electronics, we also have components with specific calibrated resistance values, called, perhaps unimaginatively, resistors. Open up an electronic device, and you'll see that they're full of them. The fundamental unit of resistance is the ohm. The unit of conductance is the reciprocal ohm, also known as a Siemens. In the neuron, we've already encountered a variety of important resistances. Each type of ion channel, for instance, has an associated resistance. The more permeable a channel is to ions, the lower its resistance. Likewise, the more channels there are in a given patch of membrane, the lower the resistance. Typically, when we talk about resistance in neuronal membranes, we measure them in ohms per square millimeter. Another important resistive quantity is the resistance through the cytoplasm of the cell. This will become important when we start talking about signal propagation later in this module. Roughly speaking, the saltier the cytoplasm is, the lower its resistance, and the wider the pipe the current must flow through, the lower the resistance. This pipe analogy is actually quite apt. In fact, it's often helpful to think about the flow of current like the flow of water. In this scenario, voltage would be the potential energy, from gravity, of an elevated reservoir of water, manifested as water pressure, and resistance would be represented as the diameter of the hose. Bigger hoses allow water to flow more easily. Thinner hoses, less easily. Likewise, in analogy to ion channel density, if we have a barrier with lots of holes in it, it poses less resistance to the flow of water than a barrier with few holes.